Well, bonjour, good morning. It is a pleasure to be here. So I'm Leon Balents. I'm a professor at UCSB, Santa Barbara, California. A little trivia about this place for me. This was the first major school I went to myself in 1993. I don't know, maybe some of you are not even born then. The place was a bit more rustic then. I was coming from Boston, where I was doing my PhD. So this was before I came to Santa Barbara. I came to Santa Barbara the following year as a postdoc. This was a fantastic experience. I camped in a tent on just above the water there, because we were very poor. Couldn't afford to stay in a hotel or whatever it is they could put us in. And there were some other people here that you might know. Also camping was Leo Radzahovsky, who was my colleague at my peer, other student in grad school. And there were a number of experimentalist students. Ali Yazdani, who you know, Cam Moeller. Aaron Kapitolnik was their advisor, was one of the lecturers. There were a number of other people. It was about superconductivity mostly and vortex physics. So 26 years later, to be back here is pretty special, very nice. So I'm very, very pleased, except for the fact that I have to do some work now. I think life as a student is a bit easier. It's okay?
Yeah, it's just one point. I've pointed that out to the other lecturers.
That this is dark?
There's a dark part.
Okay.
So this is the forbidden part.
Mm.
Use it for announcement, not for recording.
Okay, very good.
It's the other way around, so I just mark it.
Yes.
Try to stick to the
All right. All right. So this will be, I guess, a sort of counterpart to Dima Afatov's lectures last week. So I'm going to be talking about twisted bilayer graphene. That is a long thing to write, so we're going to be writing TBG. I was speaking with him earlier, and we were wondering if this might be the first time anyone has lectured about twisted bilayer graphene in a school. So it's early. It's a very new and active subject. Indeed, it might be too early to lecture about it, but I'll do it anyway. Okay. I like to think of this as kind of a meeting of two worlds. Oops, be careful. People like Dima come from graphene. Graphene is, of course, very famous. I think of it as a kind of textbook example of the power of band theory and really simple band theory. If I teach an undergraduate class on solid-state physics, it's one of the first things I do. How many of you had it in a class? Probably almost everybody, right? It's so nice as an example. I think it will do it, because anytime you teach, you have to do it. I think, as a material, it's really a kind of beautiful example of a kind of two-dimensional electron gas. So this is I'm not spelling this out, this is a conventional acronym for two-dimensional electron gas. Two-dimensional electron gases are one of the oldest subjects in condensed matter physics. It's one that was particularly important in the, let's say, the 1980s and 90s. It was, and I would say a lot of the work in graphene is kind of recreating this and revisiting what used to be the gold standard, sorry. Of two-dimensional electron gases, which are semiconductor devices made out of heterostructures of gallium arsenide and aluminum gallium arsenide. But in the context of plus a bit of Dirac physics. It's a beautiful system, particularly nice because you can make really honestly two-dimensional, not quasi-two-dimensional, not set of infinite number of 2D systems weakly coupled together. Electron systems is super clean. Seems like every year it gets cleaner and cleaner. I don't know if this has stopped yet in graphene, but this was something that was happening in these 2D electron gases in gallium arsenide. This guy, Lauren Pfeiffer, who was at Bell Labs and now is at Princeton, every year would increase the mobility of his 2D electron gases by some factor of 3 or 4 or something like that, until it was in the, I don't know, million, several million mobility, billion mobility, I don't know what it is now. Cleaner and cleaner, and somehow every time you make it a little bit cleaner, something new happens. A beautiful subject. I would say almost everything observed here, there's a lot of physics, mostly in gallium arsenide, most of the physics was related to integer and fractional quantum Hall effects, well, there's many other things. In graphene, I would say almost all of the physics is understandable in terms of electron bands, basically almost free electrons. So one electron physics. Plus sort of moderate interactions. So I kind of call this in general two-deg stuff. Okay, so what does two-deg stuff mean? It means that the only thing that you had to take out of the atomistic structure of graphene, the fact that the particular way the carbon atoms are arranged on the lattice is the low energy band structure, the fact that you get Dirac Fermions, so in graphene. But there's sort of another world. This is one world. The other world is the world of correlated electrons. Actually, most of the people talking here are kind of from that world. Okay, so these are kind of materials, not one material, but many materials with very large on-site repulsion, let's say atomic, usually, Coulomb repulsion. In which electrons may be localized to atoms or close to that. So this is the kind of physics that Giovanni was talking about. These are often sort of modeled theoretically by something like a Hubbard model. A sort of extreme example of localized electrons are spins. When we talk about just some thinking about an experimental system or a material in terms of quantum spins, what we really mean is that there are some electrons that never leave an atom. So they're fully localized, and there were and will be lots of talks. Premi was talking, I guess, about quantum magnetism. Lucille, who will start tomorrow, will talk about it. I think at least Radu and Colin's talks will be in that category. Amalia is probably somewhere in between. Here the subjects are very material dependent, and this is kind of the realm of what's sometimes called quantum materials. The subjects might be things like cuprates, high TC superconductors, iron superconductors, pnictides, etc., heavy fermion materials, which are kind of Pierce Coleman's favorite stuff, cobaltates. There's a big list, maybe ruthenidates, vanidates, all this stuff that the DMFT people really love. What sets this area aside is that compared to the left, band theory is either a very bad starting point or very strongly, can people see the bottom of the blackboard? I think so, huh? That doesn't mean you can read my handwriting. Or strongly modified by interactions. So if you actually start reading literature on iron superconductors, for example, or heavy fermions, people measure bands and they study properties of bands, but often those properties are very different from what would come out of band theory. Okay, so TBG is trying to bring these things together. I guess this is the forbidden zone here. No. Good. Bigger chalk. All right. So what these lectures are about is trying to see how we can, how experimentalists, clever people like Dima have managed to make graphene, some version of graphene, behave like a correlated material. Okay. So maybe just a few comments and caveats. Actually, when I gave the title of these lectures, I said I was going to talk about Moiré materials. So you notice graphene doesn't appear in here at all in those words. So in principle, Moiré materials is a bigger area than twisted bilayer graphene. But twisted bilayer graphene is very young as a subject, and the broader attempts to look at the effects of twisting on other materials are even younger. So I think, given the time I have and what I know, it will be hard for me to talk about more than this. But you should know that there are many other systems. For example, there are not only bilayers of graphene, there's trilayers, there's bilayers, if you can figure out what that means. People are trying to twist a variety of other two-dimensional materials. Especially interesting maybe are transition metal dichalcogenides, like tungsten diselenide, which is a very strong spin orbit coupled 2D material. There are two-dimensional ferromagnets and antiferromagnets, many interesting things that probably will occur, but I won't talk about it probably. So my point of view is going to be to try to work our way towards getting to correlated electron physics in twisted bilayer graphene. The caveat should be that, actually, I didn't see them, but you had some nice lectures last week on topological physics. This topological physics of bands is all one electron physics, and, you could easily spend an entire semester studying topology of bands. So one electron physics is still interesting. Oh no, you can't see the G, it's gone. And there's, in fact, it's even more interesting in Moiré materials. So that's kind of a comment. There's an associated caveat, which is that actually the one electron physics in twisted bilayer graphene is almost the only part we understand. It's usually the only part we understand, okay? If you ask big famous theorists like, I don't know, Ashwin Vishwanath or Andrei Bernavig, they say they understand everything, okay? But they'll say they understand everything and can explain everything, and they also violently disagree with one another. So something is inconsistent. And, you know, one-electron physics is still important. Usually, that's kind of the flavor of dynamical mean field theory is in this way, as you heard in the last talk, is that a lot of correlation physics sort of consists in trying to describe interactions between electrons in terms of renormalized one-electron problems. So in DMFT, you try to dress up the one-electron physics with a self-energy. BCS theory, which Pierce talked about on Saturday, is a way to effectively describe one particle states in a superconductor, which is where superconductivity is certainly caused by interactions, usually electron-phonon interactions, but other kinds. Every Hartree-Fock theory is a bit like this. You try to do your best job of describing an interacting electron state in terms of one-electron states. So these are examples. Maybe continue that. So examples of sort of effective one-electron problems are BCS theory. BCS is a little different because it's mixing electrons and holes, but it's still one electron problem. You still have something like a Schrodinger equation. Hartree-Fock, mean field theory, all have these character. I mean, a nice question to ask is what's beyond this? Is there physics in interacting systems that's beyond this? In correlated systems. It's kind of fully beyond one electron. There are things like this. Probably the most famous, most interesting example are things called quantum spin liquids, which you'll hear about in Lucille's lecture starting tomorrow. One-dimensional, what are called Luttinger liquids. Spin charge separation. Maybe more exotic, not so clearly defined subjects as incoherent non-Fermi liquids. So these are words you guys maybe have heard or don't know some of them, maybe don't know some of them. This part of the lecture is kind of motivation and context, okay? Are any of these really, they can be pretty exotic things going on here, very interesting types of ordered or non-ordered topological states described this way can emerge in correlated systems. To preview, some of this stuff definitely emerges in twisted bilayer graphene. Does anything this exotic, kind of the next level of exotic and crazy, emerge in twisted bilayer graphene? We don't know yet. So how does this work? You know, roughly speaking, why does twisting graphene make it correlated? Okay. I need more space. Okay, so the this, as you can ask this sort of basic question: when is a material strongly correlated? Okay, and this is a sort of question that Giovanni's lectures, I think, gave some answer to. So the basic framework, if you want, is we like to compare the bandwidth to Coulomb U, a strong interaction energy. So the basic competition in an electronic system which measures this strength of correlation is how big is the effect of interaction, the energy of an interaction, compared to energy of delocalization of electrons into a band. So you might have in mind a hopping Hamiltonian, which would be something like, have some hopping strength T, moving an electron from one site I to another site J and vice versa. So these are just electron creation and annihilation operators. If you, that's again, this is the type of problem you work out in graphene. If you diagonalize this, you get some energy bands, E versus K, which can have some pretty complicated structure, something like this. Usually we call the width of one of these curves the bandwidth W. For a simple model like this, the bandwidth will be typically of order approximately this basic energy scale T times some number, which has to do with how many neighbors roughly you have. Okay? So the more neighbors you have, the more the electron can delocalize, the wider this band is. For a non-interacting system, what you'll do is fill up this band to the Fermi energy, sort of occupy the states below here, and this takes you down in energy. This blue is bad, huh? Shouldn't use blue. Red is better. There. Red's more visible, right? You can see red? Yeah. So it's kind of, you lower the energy compared to the average by an energy of order the bandwidth, okay? By comparison, if you localize electrons, then they don't hop at all, and you don't gain any of this hopping energy. So the cost to localize is W, but you can save a repulsive energy of order U by localizing. So generally speaking, if you draw some axis U over W, when U over W is small, you have something which is band-like. Over here you get metals and insulators, and at some value, roughly of order 1, bigger than this, metals and semiconductors, things like this, you have really localized electrons, and this is where you get correlated materials kind of from here on out. Okay. So a very, very crude summary of mod physics. For graphene, these abstract orbitals, sites I correspond to some PZ orbitals. And the hopping T is actually pretty big between these. It's about 2.8 electron volts. If we draw a picture of a honeycomb lattice, you can see every site has 3 neighbors. So the bandwidth is about 3 times that. If you work it out, the bandwidth, at least for the simple band calculations of graphene, gives a bandwidth of something like 8 electron volts. And really just to preview, that's, rough picture is something like this. There are electron, conduction, and valence band. This is kind of the 8 electron volt scale. If we put them together, it's 16 electron volts. This is a huge energy. Yep.
On the previous diagram, you have the bandwidth is roughly coordination number times T.
Yeah.
On the right-hand side of the bullet, you have T is 28 electron volts.
2.8. 2.8.
Oh, cool.
2.8. Sorry. Take these as very rough theorist numbers, okay? Nobody really knows this, actually. Close enough, okay? Yeah, interactions are much harder to know. It kind of depends a little bit how you define them even. I won't even give you a number. But, you know, typically U's might be a few electron volts. Rule of thumbs are basically that S and P electrons have relatively small U. Basically, the bigger the orbitals are, the smaller the U is. You try to cram charge into a small orbital. It costs more Coulomb energy. There are very few materials where the bands are mostly built of S and P orbitals that are strongly correlated, and graphene is not considered strongly correlated. So this is sort of the problem. This is not nearly big enough for these gigantic bands to make strong correlations. Yeah?
Just a short, I mean, you can be actually in graphene quite large. It's on the order of 10 electron volts. That's roughly what people think.
Again, it depends a bit on how you define the U. So,
The problem with graphene is that the screening is not so efficient, so I mean, you need to worry about long range.
so we'll get to this. We'll get to this, okay? The discussion about strong correlations, the point I want to make is when we talk about a strongly correlated material, we really mean one where the energies are so strong locally that they can fully rearrange states throughout the entire electron band, even those, you know, rather far from the Fermi energy. We can always ask the question, what about states very close to the Fermi energy? Can those be rearranged? There's always, at least if there's no gap, you can you know, move an electron from just below the Fermi energy to just above with very little energy cost, and even a not so strong interaction can cause that type of effect, okay? So the basic problem in graphene, making graphene correlated, is the bandwidth is too big, okay? And defining these interactions is actually subtle. It depends which bands you keep, and you know, one band model, what is the right? So these are sort of theorist questions, you know. How do you actually measure U? Some parameter in somebody's model. So never take theorists' models too seriously, okay? I know 2/3 of you are theorists, so don't take your own models too seriously. Okay. So we can ask the question, you know, how could we reduce U? Reduce W. Okay, that's what we would want to do. So there's a very well-known way to reduce bandwidth, which is to enlarge the unit cell. So this is, again, a well-known strategy from semiconductors. In semiconductors, they call this making a superlattice. Okay, you guys, again, if you took a undergraduate solid-state physics class, maybe even just a quantum mechanics class, you also learned this. You learned something called the nearly free electron approximation. For bands, they probably made you draw these god-awful diagrams. You could start with electrons in free space, for example, just have a quadratic dispersion. So what's the bandwidth of an electron in free space? Well, it's infinite, because it goes up to infinite energy. Okay, how do we make it smaller? Well, we can apply a weak periodic potential in one dimension, because I like to draw things in one dimension. We can introduce a lattice spacing A. What that does is now we can think of our states as block states, and we classify them within a Brillouin zone. So this is a Brillouin Zone. No, I never have, scary to say Brillouin Zone in France. It's doomed to failure. Let's see, yellow maybe. And so what this does, you now fold these bands back. The presence of the periodic potential can open up very small band gaps. But even without worrying about the band gaps, you immediately see that a finite bandwidth is formed here, okay, W. For free electrons, this bandwidth will be of order h bar squared divided by the mass times a lattice spacing squared. Okay, and the reason is, the original parabola had a dispersion k squared over 2m, and we just set k equal to pi over a, so we get a bandwidth like this. Okay, and so the bigger you make a, the smaller the bandwidth is. So this is great. That's the whole strategy. The only real problem with this, there's nothing about graphene there. We could do this in an ordinary semiconductor, and indeed people do it, make the band narrower and narrower. The problem is when you make the band narrower and narrower, it becomes very susceptible to disorder and things like that. So what's good about graphene is you can do this very cleanly. Okay. But with graphene, there's actually a problem, kind of interesting problem, which is, we don't have a parabola, we have a Dirac. Let's try to draw the same picture for Dirac Fermions. So Dirac Fermion, at least the initial picture is really nice and easy to draw. Epsilon versus K. And now, if we imagine we create some superlattice here, okay, of course, this should really be a two-dimensional picture, but all right, I can't draw in 2 dimensions, it's a cut. We should fold back this diagram, and what we'll get is some bands like this. We may or may not open a gap here at the Dirac point, depends on details of what we do. So now you can see where the original bandwidth is something huge on this scale. If my A is large, this Dirac fermion should reconnect to another one over here in the dark zone, okay, with a bandwidth of 8 electron volts. But if we can make a large period superstructure, which is what you actually do by this Moiré twisting, then we'll get a bandwidth here. What is it? Well, again, this dispersion is h bar times the Fermi velocity times k. So this bandwidth will be h bar times this Fermi velocity divided by the lattice spacing, basically. Okay? So it looks good. The larger we make the superlattice, the smaller we make the bandwidth. So then we can just make the bandwidth as small as we want, thereby increasing interactions relative to the bandwidth. But there's sort of a problem. Again, I have trouble drawing complicated things, so I'm going to draw a simple thing. Imagine we made a superlattice that was a square lattice, because I can draw square lattices really well. All right, our little graphene is in here, okay? Oh, it's a nice little graphene. Okay. So this is of length A, and we'd like to describe this tiny band that we produce in this way in terms of some effective Hubbard model. Okay, we could think that this W here is like something like some effective Z times T effective. Okay. We need to know not only the effective W for this low energy system, we need to know the effective U. Okay. Well, the underlying interactions, as was already pointed out, they come from Coulomb repulsion. Okay. And you can ask, what is the energy cost to put one electron in this unit cell of this superlattice of graphene? And that interaction energy is going to be, per particle, will be something like the Coulomb energy to localize a charge inside this unit cell, which is just E squared divided by the dielectric constant divided by the lattice spacing. Okay, depending what kind of crazy units like, you might want to put some Coulomb constant on there. But okay. So now you see if there's a problem actually. You know, the bigger you make the superlattice, the smaller the interaction energy gets too. And actually they scale the same way. So if you use these simple estimates to estimate U over W, you'll get that U is E squared divided by epsilon A, and W is H bar VF over A. So this is E squared over H bar epsilon VF. Okay. You notice it doesn't depend on A. So whatever this is actually a kind of almost intrinsic property of graphene. Doesn't really matter how big you make the superlattice. A priori, the only thing that really matters is this dielectric constant. So if this is too small for microscopic graphene, it's not going to be any larger for a superlattice naively. Okay. So why does twisted bilayer graphene interesting? Okay. Well, it's because there's a little bit of magic. We need magic. These arguments are very crude. I use tilde everywhere. Okay. A real theorist does calculations, unlike what I'm doing here, just waving my hands. Okay. And if you do a real calculation, you will certainly find that the bandwidth is of order this, but it'll be multiplied by some dimensionless quantity, which is actually a function of, we'll see two kind of very important parameters for twisted bilayer graphene. One is the interlayer tunneling, electron hopping. So if we bring two graphene sheets together close to each other, electrons can move from one layer to the other. They do it pretty fast, but not nearly as fast as they move between carbon atoms in the same sheet. So this is kind of a small parameter. And the other energy scale is this one, this naive mini band scale. And so actually the bandwidth is a function of this quantity. This quantity turns out to be sometimes very small. Okay, so the magic, the miracle, okay, and this is where the one place so far in this talk where I wish I could show a plot, but I'm too lazy to do that. I'm going to draw one. I'll attempt to draw. So if you should really look at the papers. Okay, I think the first person to really realize this miracle were Bistritzer and McDonald. They have a beautiful paper in PNAS. I don't remember. This was already quite a while ago, maybe 8 years ago, something like this. I don't know when it was. Okay, somebody knows. This would be, Google this paper. You'll find many, many, many hits. Okay, great. And what they did was to figure out how to actually calculate not only the bandwidth, but the whole band structure. And I'll explain to you how this works. Maybe tomorrow. No, not tomorrow, definitely. Maybe Wednesday or Thursday. Maybe Wednesday, if not Thursday. And what they showed is that, so the way you vary this A here is by varying the angle. So this is kind of inversely proportional to 1 over the twist angle. And for kind of most twist angles, this indeed works. If you kind of plot these bands, they look something like this. So this energy is indeed, basically H bar VF over A. So this is like if you take an angle of maybe 5 degrees, something like this, but there's some special angles, theta about 1.1 degree, where, and then there are more bands, okay? where most of the bands still have this bandwidth, but there's some tiny ones here, really tiny little things doing something. And then the other bands have this kind of bandwidth. So this is h bar VF over A, and here there's some tiny thing where this F might be really small, might be like 0.01 or something, very tiny. Okay. So that's the magic. That if you're very careful and you're very lucky, there are special twist angles. They're called the magic angles. Where the bandwidth becomes very small. And this is some kind of quantum interference effect that's special. And when that happens, it doesn't matter anymore that the effective interaction is also getting small. It's not getting small nearly as fast as the bandwidth. Okay. So that's the trick. Once you do it, all kinds of cool stuff happens. As usual in a correlated electron system, basically all hell breaks loose. And things get exciting and theorists get interested and also ineffective. This is kind of the introduction, okay? My plan is now I'm going to tell you what I'm going to actually do. We're going to start with talking about a bit of a review of graphene fundamentals. I've already managed to kill a lot of time. I'm really impressed with myself. Then we're going to explain how this happens. I'm going to tell you, basically, give you a simple derivation. Of this Bistreitzer-McDonald model. There won't be much that's new in these lectures. You know, it's a school, so I'm telling you things that people know. But this is something I don't think people know. So I've been racking my brain to find a less technical derivation of this. So I think I have a good one. From this, we can get some hint of what these magic angles are. Then I want to come back to the materials and talk about experiments. You know, this is a theoretical story, you know, well in advance, maybe 7 or 8 years before anyone actually managed to achieve this magic angle graphene. So it's a lot of theory. How do you know it's even right? Is this true? We have pretty good evidence that this part of the story is true. I'll explain why. And then I'll very briefly point out maybe special features of these flat bands. Yeah, so these are called flat bands. Sometimes people make it one word. I really don't understand why they do that. You see many papers where they write flat band as a thing. Don't do it. It's stupid. It's stupid. It's ridiculous. I know you don't. Many of you, English is not your native language. Arguably, English is not my native language. American English is my native language. However, flat bands should be 2 words. You can save the whole community by doing this. And then we'll talk about interactions. You know, what's the goal of this? Well, we'd like to understand what is going on. Dima showed you some really beautiful data showing all kinds of amazing things, superconductivity, correlated insulators, ferromagnetism, maybe more amazing things going on. To understand all of these things, any of these things, we need to think about interactions. So the caveat again here is actually nobody knows, okay? From here on, this is somewhat speculative, okay? The best I can tell you, because nobody really knows what's going on, is what are the ingredients? I'll do my best to try to describe what we can say safely about interactions. If the 2/3 of you who are theorists want to think about this problem, what are sort of reasonable starting points? What we do have more and more are experiments. And what can we learn from them? If I have time, the very last lecture I'll talk about some particular experiment that I had the pleasure of being a little bit involved in, at least helping to interpret a bit, which are some nice experiments. Again, Dima showed a little bit of that on quantum anomalous Hall effect. So I'll talk about that. Okay, so that's the plan. That was probably, all of that was supposed to probably take 15, 20 minutes. You can see how well I'm doing. But I'm trying to keep you entertained at the same time. So everything else will be just an exercise to the students. So now we're going to dig in. Any questions? Major, big conceptual questions? Language questions? No, okay.
So the effective interaction that you were talking about, are
Yeah.
you just promising us at this point that's not renormalized as much as the bandwidth is by the twisting?
Yes.
Okay.
Yeah, I mean, so basically, the basic physics of this is it's long-range Coulomb interaction. So no matter what kind of quantum renormalization, things that go on, if Maxwell's equations still hold on macroscopic scales. So if you actually pack some charge into a region, it is going to cost a capacitive energy. The only thing at play is dielectric constant. And in a two-dimensional material, it actually is very hard for a 2D material to screen the electric fields produced by charge because they mostly go into 3 dimensions. Okay, so that's the physics. Okay, bandwidth is some electron hopping property. It's fully quantum. It depends on quantum interference and things like that. Coulomb energy isn't. Short distance stuff, yes. So the U, when we worry about a U, on the lattice scale, this is a big effect. But good question. Yeah. We will eventually have to talk about that sort of thing, and I'll come back to that point. Okay. Great. All right. So the plan now is to go back to Graphene Fundamentals. Start the first one. What do you need to know? Okay. So there's a million references on graphene. At some point, maybe I will share with you some of my own lecture notes from one of my classes that has some of this stuff. These lecture notes are probably not fit to be shared. They're too terrible. There are many papers. I would, probably the go-to reference, which is a little bit old now, but it's good enough for most of what we'll talk about, is Reviews of Modern Physics article by Castronetto and Company. It's an RMP 81-109. Okay, so 10 years old, but it has pretty much everything I think you need to know about graphene. So let's start with single layer graphene. I think in view of the time, I'm going to skip a lot of details. Hopefully you guys have seen it all before, all right? I do kind of need to draw this picture. You have to establish some conventions. These are going to be the conventions I use. I don't guarantee full consistency, but more or less. So we'll start with this standard sort of picture of graphene. We have to label the sublattices. I'll label them like this. There are 2 sublattices. The site at the kind of on this lambda, it'll be an A, and on this Y is a B. And they alternate.
I'm sorry, that red over the white is not clear.
The red is not clear.
The red over the white is not legible.
That's just terrible.
Thank you.
How about this?
That's great.
Is that great? All right, you only need to see 2 of them. Okay. Okay. What is legible? Purple? No, it's bad. We need yellow. Anyway. Good, all right. A little geometry is probably useful too. Well, I'm going to skip most of it though, I think. Going to probably not need most of it, so let's try not. And we're going to just really take a type binding model with just nearest neighbor hopping. It's a good starting point. Hopping just occurs between electrons at the same spin. And then one can go to Fourier space. The way we'll do it, bless you, can define a unit cell like this. It's just my arbitrary choice of unit cell. Okay, so these, I index the every site by a coordinate r, which is the center of a unit cell, let's say the center of a hexagon, and then there are two sites. This will be the A site and the B site. So this is this coordinate r, and S here can be A or B, which I'll also take plus or minus 1. Okay? And we can use Bloch's theorem. We write this as 1 over square root of the number of unit cells, or maybe number of sites, I don't even know, of a band operator. It creates a Bloch state at momentum k and on sublattice S times e to the I k dot r. So to the students, this is something that used to puzzle me a long time. When I was a student, I always did it like this, and then sometime toward the end of graduate school, somebody showed me I could make my Hamiltonian simpler by, instead of putting r here, using this r, I would just use the actual location of the site. So we could have, these two sites would have a different r. They'd just be their position in real space. And that does make things simpler, but it leads to some complications for the theorists. If you do that, then actually the Bloch Hamiltonian's not periodic. So it's not so nice. So we'll do this. If you do this, then you can find this kind of almost diagonalizes the Hamiltonian. This Hamiltonian can be written as a sum over k, S and S prime, CKS dagger, some little object, HSS prime of k, CKS prime. And this H is now just a finite matrix. H of k. This is kind of the one electron Hamiltonian. It has the form of some function of k. So this matrix has this form because the nearest neighbor hopping is always between two different sublattices, only connects A and B. Okay, so there's nothing on the diagonal. And this is some complex function f, okay, which you can find in your textbooks, or you can work it out. So if you want to diagonalize this matrix, it leads to two energies, which are just plus or minus the absolute value of this function. Okay, that's easy to show. All right. So then it's clear, whatever the dispersion looks like, which looks something like this. All right, this is cartoonish again, taking some cut through two-dimensional momentum space. Anytime there's an energy E, there'll be another state with energy minus E. Okay, and these two energies will always be separated by a gap, 2E, except when this energy E is 0. Okay, so that happens only when F vanishes. So these touching points happen when the function F vanishes. And F is a complex function, okay? So it has a real and imaginary part. Both parts have to vanish, all right? So if you think about sort of the mathematics of that, okay, we have two conditions for f to vanish. The real part should vanish and the imaginary part should vanish, and f is a function of two variables, kx and ky. So you have kind of two equations and two unknowns. You expect you get some discrete set of solutions. Okay? And indeed, that's the case. What actually happens if we draw, this is the Brillouin zone. What am I doing? Okay. This may be important to establish this. So this is K space. Here's the origin. We have a set of reciprocal lattice vectors here. Okay, these are reciprocal lattice vectors, G1, G2, etc. Out here. As usual, you form the Brillouin zone by finding the set of points closest to the origin. And this function f, it vanishes here. That's called the k point, and it vanishes here, called the k prime point, which is actually just minus k. And there are actually three copies of this k point. These are all k points because these are reciprocal lattice vectors. The vector from here to here is G2. The vector from here to here is G1. Okay. So the open circles are the k prime points and the closed circles are the k points. So there are two inequivalent points in the Brillouin zone where this vanishes. Yeah, now it's about an hour, right? And I should take 20 minutes and then leave 10 for questions. Is that roughly? Yeah. Good. I need bigger chalk. There we go. Okay. So these are the famous Dirac points. We usually call the two Dirac points valleys. Okay. So the low energy states, in addition to being described by their momentum, if we kind of just look at them, the states within a certain range of energy around the Fermi energy, that would correspond to a sort of circle around one of these points, and there are two such circles, so there are two valleys. If you look at this function f, if we consider its behavior locally, at k it vanishes, so we can Taylor expand it around that momentum by a small momentum k. And this turns out it's linear near where it vanishes. And it behaves like this. It's linear with some slope that defines the Fermi velocity. And the sign of the slope in the x direction depends on kx, which is kind of obvious from this picture. Right? And the sign in the y direction, it's imaginary in that part. And that doesn't depend. Okay. So this linearity of f means that the energy, is plus or minus Vf modulus of k, and that's this Dirac dispersion. Okay. So we can also write down a Dirac equation that's going to be useful. So the way we do that, we go back to our expression here, and we realize that in the sum over momentum, if we only want to study the low energy states, we just need to consider the k's which are near these two valleys, near k and k prime. So there are sort of two parts of this sum, the sum inside this circle and the sum inside that circle. In the sum inside the right-hand circle, I should express little k. Sorry, this is confusing because I use k for both variables. Well, get used to it. We should expand this momentum around big K. In the left circle, we should expand it around big K prime, which is minus K. So it's nice to write this as the following thing. Okay, so I've pulled out this factor which oscillates very rapidly on the lattice. Okay, this k is basically of order 2 pi over a, so this thing varies rapidly on the lattice. And then I have sort of slowly varying parts these very slowly as a function of r because the corresponding momenta should be close to these points. So you take this and you plug this into here, insert this into this formula, write it out explicitly, and then assume that psi is slowly varying in space, and you could do some gradient expansion, and what you'll find is this Dirac Hamiltonian. Convert the sum to an integral. It looks like this. I will explain a little bit these notations. Okay, so this is going to be important. Some of these notations, they're helpful. So V is VF. I often drop the F, okay? It's just velocity. So there are a bunch of indices here that we carry around with each other. This is kind of important to keep straight. These indices describe degrees of freedom of the electrons. So I already introduced S, which could be A or B, or 1 and -1. This describes a sublattice. Okay? And to avoid writing this index, I'm going to often introduce matrices that act on this space. So I use a matrix tau. Pauli matrices tau, its indices are these sublattice indices. Okay, so if you look in this expression, there's a tau x here, or here, and tau y here. So we have something like psi dagger. Let's look here, tau y, or tau x psi. What this means, really, is we'd have an S and an S prime here. And tau x is the Pauli matrix. These are Pauli. So tau x, everyone should be familiar with the Pauli matrices, I hope. So tau x is this matrix, 0, 1, 1, 0. So this just means we have a psi A, psi B, plus psi B, psi A. Okay, because this matrix is equal to 1 when S is equal to A and S prime is equal to B and vice versa. All right. The tau y is similar, except there's some i's in there. Okay. All right. There's another index that I'm not writing yet, which is K or K prime, or I'm writing it as plus or minus. This is the Valley index. Okay, that's what I wrote here. We need to specify whether we're taking the low energy electrons from the K or the K prime Valley. And again, I don't want to write that every time, so I introduce some other matrix, another set of Pauli matrices, which act in this Valley space. Okay, so that's where this mu z is coming from here. This mu z. Mu z is plus 1 for the K Valley, and minus 1 for the K prime Valley. And if you look here, remember this function, f was linearly dependent on momentum. It was plus kx for the K Valley and minus kx for the K prime Valley. And that's exactly what's appearing here.
There should be another wave function.
I'm sorry?
Last line there, shouldn't there be another wave function on the right?
Yeah, I think I erased it when I was clearing space. Yeah, for sure. Yes. Good. Anything else? Good. Okay. And I haven't written it yet, but if we may also need an actual physical spin. And when we do that, I'll use a Pauli matrix sigma. Okay. So these different type of matrices will appear, and maybe even something worse will appear later. Okay. So, sorry, I don't know about fully consistency, but this is one of the most confusing things about graphene and bilayer graphene. There are a lot of different working parts, okay? It's just kind of algebra and counting, but you have to think about it. Okay, so if I just focus on, let me go back here. If I just focus on one of these valleys, and one spin, let's just take, this mu z equals +1, so the k valley, then our little Hamiltonian here is very simple. It's actually just v k dot tau. So this is kind of the simplest example of a Dirac equation in real space, minus I v tau dot gradient. This is a Dirac Hamiltonian. And that'll be very useful. They have very nice properties. One thing you should know is that V is big. It's something like 10 to the 6 meters per second. So it's only about 100 times, 300 times slower than the speed of light, maybe a little slower than that. So these Dirac electrons are very fast. That's related to the fact that the bandwidth of graphene is huge. Okay? And so what it means, the fact that it's so big means that I just move a little bit away in momentum space, from these k or k prime points, the energy of these electrons becomes enormous. So when we're going to study low energy physics, which is what we do in twisted bilayer graphene, those high energy electrons are not important. So the only ones that are important are the ones very close to these Dirac points. And so to a really excellent approximation, we can think about our energy momentum dispersion is something like this, okay? Just two Dirac cones at k and k prime, and in this formalism, those Dirac cones are just different flavors, if you want. They're different valleys, okay? So I guess, how much time do I have left? 10 minutes or so? Yeah. Okay, so I think a nice thing to do at this point is to ask, so this has been, theory, okay, it's like undergrad theory, but still theory. How do we know it's actually true? Okay. So graphene has been, they wrote a Reviews of Modern Physics article 10 years ago on it, so this must be pretty well established. How do we actually know it's true? Okay. How do you actually know you have Dirac electrons in graphene? You might well be suspicious. One reason you might be suspicious is that because of the simplicity of the model I wrote down, there were no terms on the diagonal here. So it's pretty easy to get these two bands to touch. I just had to make F vanish. If I start putting terms on the diagonal here, then to make two energy eigenvalues come together, I actually need to impose not two conditions. So I had two conditions. One was the real part of F is 0 and the imaginary part of F is 0. If I put terms on the diagonal, I have to impose a third condition, that this number is equal to this number. And now suddenly it starts to be problematic. To get these two bands to touch, I have to satisfy three equations, but I only have two unknowns, kx and ky. So you might think that it's really an accident, a mistake of my approximation, that these bands touch. Now, of course, electrons could still hop to second neighbor sites, do something more complicated in graphene. Why does this, is this even correct? If I did a real calculation, an ab initio calculation, DFT calculation, would I find that actually they don't touch? Okay. And this is just theoretical BS. How do we know? Okay. So, the best way we know is really that there's experiments, okay? And there are many experiments that really show this is true. Probably the simplest thing, and it will be useful to understand later experiments on twisted bilayer graphene, is to talk about quantum oscillations. And Landau levels. Okay. Let me remind you, there's a standard Landau's problem of free electrons in a B field. Okay. Landau solved this problem. You just write h bar squared over 2m, grad minus I E A squared as your Hamiltonian, okay? And you solve, you take that B equals curl of A is a constant. You did this in quantum mechanics class, I'm sure. And Landau tells you that the energy levels are those of a harmonic oscillator. They're highly degenerate, and they're equally spaced levels by energy h bar omega c. They start at a 0, 1, 2, 3 upward going Landau levels. Okay. So let me see how I do this. So if you study the resistance of metals in a magnetic field, what happens is, if you put the Fermi level somewhere here, in between these Landau levels, then there are no energy states around, so the resistance is actually low. It's hard for those electrons to scatter. When they sit over here, the resistance is higher. In general, the density of states oscillates. It looks something like this. In a real system, these things get broadened. So what you can do in an experiment, a nice thing you can do at least in theory, which you can actually do in graphene, is make a plot like this of magnetic field versus density. Suppose we have no electrons, then the Fermi level lies down here. We don't occupy any states. If we put the Fermi level up here, then we have to fill a Landau level. So the number of states in a Landau level is the, somehow, when you get in front of a board, everything, you become stupid. I don't know what it is, but you really do. Yeah, B over phi naught, okay. Is basically the number of flux quanta you can fit in the sample. If you divide by the sample area, it's the magnetic field divided by the flux quantum. Phi naught is h over E. And in general, if there's some degeneracy of the Landau levels, this will be multiplied by some factor p. For example, for just free electrons with spin, it would be multiplied by a factor of 2. That's, we can fit both an up and a down spin electron in every little cyclotron orbit in the Landau level. If we go up, here we'd fill 2 Landau levels, so it'd be 2b over phi naught p. Here would be 3b over phi naught p. And so if we plot some quantity which is sensitive to the density of states, which for example has a minimum at this, when the density of states is a minimum, then we'd find that this would occur on straight lines. So this is a straight line in this plot. This is, n versus b, or b versus n has a certain slope, all right? And there'll be a set of equally spaced lines like this, okay? 1, 2, 3, something like this. Yeah, okay. I don't know, somehow my luck drawing is opposite to how I want it. I don't know why. Okay.
You wanted to put it there to plot energy.
No, I don't want to plot energy, because it's hard for experimentalists to measure energy. If you can imagine, a more physical thing maybe to imagine, I'm rushing now because I don't have a lot of time. I think I better figure out how to do this in a...
No, it's 1 over... What do you want to plot? You want to plot the quantum oscillations? The position of the maximum of the quantum oscillations?
Could be.
Or the fan diagram? This is a fan diagram.
Yeah, I want to plot this, yeah. 'Cause this is usually what you measure in these bilayer graphene experiments. So here the density certainly behaves like this. It seems okay when I'm writing, but normally somehow I go up. But yeah, it's 1 over p. Sure. Well, all right, fine. I won't get there anyway. Let me come back to this Venn diagram, okay? Because I don't have time, and I won't be able to get to the explanation for the Dirac electrons anyway. Let me instead talk about Hall effect. Okay. So if we go to very low temperature, then we develop this very famous phenomena of integer quantum Hall effect. Of course, we can try to imagine plotting sigma xy versus density. We can't have less than 0 electrons, so there's no region here. All right. Of course, it's 0. At some point, if we start filling this Landau level, we go above this Landau level, it'll take a jump, and it reaches a plateau. And that plateau is associated with one filled Landau level. So this, the value here, maybe it's better to draw like this, will be, again, this degeneracy factor times e squared over h. Okay. I'll come back to explaining this a little bit more later. And then as we go higher, it'll take another step, and it'll go to 2, p, 2p, 3p, just makes uniform steps like this. Okay. This is actually a very hard experiment, not an easy experiment to do, okay, in an ordinary electron gas. I can do it. In graphene, we have a slightly different problem. Instead of Landau's problem, we want to study h equals minus I v tau dot grad minus I EA. Okay, there should be some h bars scattered in here somewhere. Okay. So this is a Dirac equation in a magnetic field. Okay. And this actually leads to Dirac Landau levels. I was planning on doing it in front of you, but I think I won't, clearly now. It's a kind of classic problem. It's not too difficult to solve. And what you find is that the energy levels are, let's see how I want to write it. How do I write it? Yeah, okay. They have a different structure. Again, they depend on some integer index n. They vary as square root of n. And instead of this cyclotron energy, what appears is energy V over L. Okay, there should be an H bar here, I guess. Where L is the magnetic length. So B times 2 pi L squared is the flux quantum. So this corresponds to L is square root of H bar over E times B. Okay. So compared to this spectrum, the Landau level spectrum of graphene looks a bit different. You have a, let's use red, a Dirac electron. You have a 0th Landau level, but you have Landau levels on both sides. Shouldn't be surprising because the Dirac electrons disperse both up and down. And the spacing's not uniform. So this is the smallest spacing. The next ones are a bit further apart, et cetera. Okay. Oops, sorry, I didn't mean to erase that. Okay. So now we can try to draw the same plot. Sigma xy divided by e squared over h versus n. What do we know? Well, if it's at 0, if we have 0 electrons, it means at charge neutrality. You're well aware that the Hall effect is used to distinguish electrons and holes. You get a positive Hall coefficient for holes and negative for electrons. Something called particle symmetry basically guarantees that this will be zero at zero density. But now, what happens is as soon as you go to positive density, you start, so you move the Fermi level up here, you've filled the zeroth Landau level. You go here, you go below the zeroth Landau level. Actually, what happens is something like this. The Landau level physics tells you that every time you fill one Landau level, you change the Hall conductivity by 1 e squared over h. So going from negative density to positive density changes the Hall conductivity by 1 e squared over h. Since the curve is symmetrical around 0, it means for every filled Landau level, we get half e squared over h above and half below. So this value is actually whatever this degeneracy factor is divided by 2. And this is minus p divided by 2. And then it comes up again, so we add another p e squared over h, so we get 3p over 2. And minus 3p over 2 here. For single layer graphene, this degeneracy factor is 2 for spin times 2 for valley, because we had 1 Dirac cone for each valley and 1 for spin, so this is 4. So actually this plateau is 4 divided by 2 is at 2e squared over h. This is 6. The next one will be up at 10. Okay, so you can see each step here changes by 4e squared over h. Okay. But the peculiar feature is the fact that the lowest 2 plateaus occur at 2 and minus 2, and there isn't one at 0. Okay. The reason there isn't one at 0 is if you put the Fermi level in here, then you're not in a gap. Okay. This is the kind of thing that was observed in the very first measurements of integer quantum Hall effect on single layer graphene. Eventually, samples got better, people went to lower temperatures, more complicated things happen which are related to interaction effects. Okay. But this is the most basic difference. If you compare this picture to this picture, there's sort of this 2, which is a half of 4. That half is the signature of Diracness in this type of experiment. Okay, I think I should stop here. The next time I'll pick up with these, a few more fundamentals, and we'll move on. All right, thanks. Sorry for going a little long.